is Professor Elihau Cohen, and he'll be speaking on non-inertial quantum clock frames leading to non-Hermitian dynamics.
Thank you. And I'd like to thank Thomas for the major efforts for bringing about this excellent conference for the 10th time. This is a major achievement for persistence. And today I chose to speak about a topic in the interface of quantum mechanics and general relativity, as probably I should in this conference. And it was mainly done with an excellent postdoc in my group, Ismail Lucas de Paiva. So many of the results here are due to him. And before starting, I just wanted to say a few words because not everybody knows Bar-Ilan University. So it's located at the center of Israel, pretty close to Tel Aviv. And my group at Bar-Ilan University is called From Quantum Foundations to Quantum Technology. And in this slide, I grouped a few pictures from some recent work we have done regarding quantum foundations. So we are interested in entanglement and non-locality, traditionally in weak value and weak measurements, since my PhD with Aaron. Today I'll talk about quantum time, but the main goal is actually information-based approaches to quantum gravity. This, by the way, was performed together with Ido Kaminer, who was here. So, yeah, I'll speak mostly about quantum time from a quantum physicist approach, but the real goal is eventually quantum gravity above. And on the technological side, we are interested in computation, communication, and mostly sensing. So here are some examples of the works with Marco Genovese, and who will speak afterwards. But now for the main topic of today, I'll start with a brief introduction to the so-called problem of time, and also a brief introduction regarding time-energy uncertainty relations in quantum mechanics. Then I'll tell you how people before us and also my group used the Page and Wooter scheme for addressing these three topics. Then I'll arrive at what I see as the major issue here, at least on the fundamental side, which is the general appearance of non-unitarity in accelerating and gravitating clock systems. And if time lets me, I'll also spare a few words about what we call dynamical non-locality in time, which also arises from the same framework. These are based on some pretty recent results. The second was actually accepted only this night. So yes, these are the papers. And now the background. So the problem of time is mainly about the discrepancy, I think, between time in quantum mechanics and in general relativity. There's an apparent conflict between the role that time has in these two fundamental descriptions of nature. And in quantum mechanics, we know time as some external parameter. It's unaffected by the system, and it's also universal and absolute for all observers in most frameworks. However, in general relativity, time is part of space-time. It has the same role of space. It's just one out of 4 dimensions, and it is affected by mass and energy. Moreover, and unlike quantum mechanics, time is dynamical and also relative. Different observers have different notions and different experience of time. And in this regard, the Wheeler-DeWitt equation, which was beautifully described yesterday, is phrased as follows. And one can easily see that there's no time. Apparently, only apparently, there's no evolution. We don't have the time-dependent Schrödinger equation. So something might seem to be missing in this description. Now, slightly diverging or trying to address these problems, one may try to define a time operator in quantum mechanics. We know about X and P, these are self-adjoint, canonically conjugated operators, so what about time? Is it the canonical conjugate of the Hamiltonian? But as we said, time is typically understood just as a parameter. It's not a dynamical variable. It doesn't belong naturally to an operator. So, although this could have been instructive, as I will show you next, due to Pauli mainly, this reasoning was abandoned for several years because it was believed that if H and T obey this commutation relation, then the Hamiltonian would be unbounded from below and the system would be unstable. It will always try to go lower and lower and lower ad infinitum. Nevertheless, we showed previously, Page and Wouters and many others have addressed a way in which we can define a time operator via an external clock, and we do get some notion of dynamics, which I'll discuss in a minute. So I won't stop at the Page and Wouters scheme. I'll then add another clock, and I will let the clocks accelerate. But still, what I'll show you would be Newtonian and maybe relativistically inspired, but we don't yet have the quantum gravity description of all that. Okay, so what's the main idea behind the Page and Wouters scheme, if you haven't heard about it? We start with a large system, and we divide it into a subsystem we call a clock, and all the rest is what we are actually interested in, and this is the system of interest. So although we have this Hamiltonian constraint, H psi equals 0, we do have the Schrödinger equation, the time-dependent Schrödinger equation for the subsystem called rest. I'll show you this in detail. And interestingly, this was also demonstrated in the lab, again by the Genovet group. And these are two examples of figures from their papers. And this scheme has recently been of great interest. I think this is now an active research topic. So it started from the works of Page Wouters and then Giovanetti, Lloyd McConnell, and then Marletto Vedral, but now there's really a huge interest in this framework. Okay, so let's start now the mathematical description. We have this black box, and maybe there's a problem with the graphics here. Let's see how severe it is. Oh, yeah, it is pretty severe. No, okay, it's just this line. Okay, I can manage. Okay. Okay. So what we have is the Wheeler-DeWitt equation, and then Page and Wouters divide the large system into two subsystems, A and R. And for these two systems, H, the total Hamiltonian, is separated into H of the clock, which I call A, HR of the rest, and some potential interaction between these two. So this is how the Hamiltonian constraint looks like. And now we may project on some eigenstate TA of the clock, bearing in mind this important natural relation between HA and the time derivative according to TA. And once we plug HA as I H bar D to the TA of psi, then we rederive the Schrödinger equation. So we didn't have dynamics, but now we have, thanks to this external clock with Hamiltonian HA And this also induces some effective dynamics from the perspective of clock A, where we single out HA and we only have the Hamiltonian of the rest and some interaction between them. So this is the story. We have something like psi double cap, and then we project it each time into some time of interest TA, and the projection is the usual wave function psi of TA. Is this okay? Yeah, familiar. Okay. Now what we are going to do after Bruckner is introducing another clock. So we have this internal clock A, and now we have an external clock B. And the procedure is similar. We just have a larger Hamiltonian now, including also HB, and the interaction Hamiltonian, which also depends on TB, but apart from that, the story is the same. And now we can define the effective Hamiltonian when tracing out clock A, but also the effective Hamiltonian when tracing out clock B. Already in this scenario, the two clocks may have different uncertainties regarding the time they show, but up to our work, I think they were synchronized and there were no special effect. Okay, so this was the background. Just to finish the background, what we have is a clock. It has its observable TA, so it's not a canonical conjugate of H, the Hamiltonian of the system, it's its parameter. And now it obeys what we call the covariance under time translation, so it obeys this natural equation. And the wave function, as I explained earlier illustratively, can be defined as this. This is the wave function, and it is composed of all instances of time integrated. Now this is just a formality, but actually TA needn't be a self-adjoint canonically conjugate to HA. TA can be constructed as a P of M, and for the main results I will show you, it can be constructed this way, but in the literature it is often defined as an ideal clock, which means what you expect it to mean. TA and HA obey this commutation relation. TA is actually an eigenstate of TA, but this is not necessary. And HA is defined as this time derivative. So if you want, for simplicity, you can have this picture in mind, but recall that this belongs all to the clock, not to the system. Okay, now the second part of the introduction belongs to time energy uncertainty relations, and here I'll be super brief. You can define them in various ways. The way that I treat now a time energy uncertainty relation is basically the question, is there a minimum duration for performing an energy measurement? Can you do an energy measurement which is arbitrarily fast? Here there's a famous inaccuracy of Landau, because he thought that there is such a time energy uncertainty relation. But 30 years later, Aronov and Bohm showed that this is not quite true in a general scenario. When you use an ancilla and a potential compensation for the interaction, you don't get time energy uncertainty relation, at least in this sense. Now also this is not quite the full story, because if you don't know the Hamiltonian that you are going to measure, then you need to spend some time learning it. So there was this refinement and also another refinement regarding an internal part measuring the energy of the rest. But still, the bottom line was that the measurement can be performed arbitrarily fast if you know the Hamiltonian. So before we started the work, this was what we know and don't know about all cases. The measurement can be carried out by an external or internal system. We can optimize or minimize for the time as shown in the external clock or the internal clock. The Hamiltonian can be known or unknown, and I'd like to focus on the case where the Hamiltonian is known. So what I'm going to show you is how we found out those two question marks, how we replace them with a yes-no answer. So now we'll have this system R, and this system R will be measured from outside using this measurement device E. The measurement device E will have its external clock A, and there's also an internal clock B inside system R. This means that the Hamiltonian of system R is composed of HB of the clock, HS of the system, and some interaction with the external system. The interaction now would be the von Neumann interaction used for measuring the energy. So, as we always do with the von Neumann Hamiltonian, we have some window function or coupling function G of TA. We have the parameter that we want to measure. In this case, we want to measure energy, so it's HR. And we have PE, which is you can say the momentum of the pointer of the measurement device E. The total Hamiltonian is then HA plus HR plus H of von Neumann. And the effective Hamiltonian, once we trace out the clock, the external clock, looks like this. So this is the external Hamiltonian. And now we can ask how time changes in system B from the perspective of clock A. Because remember, this is a measurement carried out by an external system. So the time is given by an external clock, but the measurement is of an internal system with its internal time, TB. And this leads to an uncertainty relation. We see that there is a minimal duration for completing the energy measurement of this system. So whenever we perform an energy measurement using an external clock, we do have a time-energy uncertainty relation. The measurement cannot be performed arbitrarily fast. Even more interesting, I think, is this effective Hamiltonian. Why is it interesting? Because it turns out to be non-Hermitian. So when we view the Hamiltonian from the perspective of the internal system, of the internal clock B, we see that the Hamiltonian is non-Hermitian. And this will return several times in this talk, because we believe now that this is a general feature, either of the Page and Wooter scheme, or even more than that. Okay, so this was a measurement performed by an external system. Now we can analyze the remaining case of an energy measurement performed by an internal system. So when the time is given by an internal clock B, we can do the same procedure. We have the Hamiltonian of the system, we have the von Neumann Hamiltonian. In this case, I needed to symmetrize the von Neumann Hamiltonian because G of TB may not commute with HR, so it is symmetrized. And now the total Hamiltonian is HT. When we trace out clock A, we get the effective Hamiltonian from its perspective. But now there are no time-energy uncertainty relations. Now we can do the measurement arbitrarily fast. So if we measure the energy of the system and we try to optimize for an internal time, then there are no time-energy uncertainty relations, but the effective Hamiltonian from the perspective of the internal clock is still non-Hermitian, and now even we have this explicit contribution of a non-Hermitian term in the Hamiltonian. Okay, so just to summarize, we can now replace these two question marks by a definitive answer. There is an uncertainty relation when we try to optimize the internal time using an external measurement device, and there is no time-energy uncertainty relation when we try to optimize an external time using an internal measurement. So this was the first part,
Eli,
and probably the longest. Yes, Raj.
would you show us in some elementary way how you derive a non-Hermitian effective Hamiltonian, whereas you only do a trace, and the trace in the textbooks cannot lead to any non-Hermitian.
Right.
What's the mechanism, if it can be explained in simple terms?
Yes, I'll try. So the issue is here we have some non-commutativity between the interaction and the Hamiltonian. So it's not just we trace out some systems like A and B, we trace B, but the operators of B and the operators of A are commuting, so there's no problem. Here, when we trace out, we still have some interaction term, and the interaction term does not commute with the Hamiltonian. When we trace it out, we are left with something, and this something is non-Hermitian. The detailed calculation is, of course, detailed in the manuscripts, but yes, for the interest of time, I'll try to be quicker. Maybe in the next examples it will be clearer how we do it. Okay, so we saw that once we have some interaction Hamiltonian which accounts for a measurement, we get this non-Hermitian Hamiltonian. Now the question may rise, how general this is? And the natural thing to think about, I think, is acceleration or gravitation, because we know about the terms for gravitationally related collapse, and there are some expectations in quantum gravity to see non-unitarity, so we started moving slowly in this direction. So now we have some Hamiltonian over free particle, but when we start to make things spatial relativistic, okay, so first, yes, we include this potential V of x. V of x just accounts for the acceleration A, which may not be constant. And now I want to include the rest mass within the Hamiltonian, which means that instead of mass m, I have the m plus h, the energy, divided by c squared. So this is the relativistic correction, the very naive one, which we'll use now. And in this case, the symmetrization of the interaction with the Hamiltonian looks like this. I remember that f of x is the result of some potential accelerating the clock. And the effective Hamiltonian, yet again, fails to be Hermitian in general. So I know that this is, it might be hard to follow all the derivation and all the math, but I want to focus on the message and to consult with you about the message, because here too we see a non-Hermitian dynamics, and it is divided into cases. So if we have these two spaceships and they don't have any acceleration, then everything is Hermitian. If there is no external potential, which is non-commutative with the Hamiltonian, then everything is Hermitian as we expect. Time propagates in a similar pace from both perspectives. However, if system A, if clock A begins to accelerate, then when we trace out over this system, the effective dynamics for system B will be non-Hermitian. And of course, if both systems accelerate, then the dynamics is seen as non-unitary unitary from both perspectives. So this was the case of acceleration, pretty similar to the case of measurement. And here too, we can give another example of a specific potential, Newtonian attraction between two systems. So here it's a one-dimensional problem. For simplicity, we have these two methods of the two systems, each including its own clock. The interaction is again represented by this, so the Hamiltonian over C squared replaces the mass in the formula. This may seem strange, like Bruckner used it in several of his works, and I think that at least to some order it should be okay. Then when we plug in all the H's within the potential, the attraction potential, we get this simplified function f of xn, hb, and so on. But the thing is that now the Hamiltonian contains this function f, and f depends on xn. So f depends on xn, but we have here hn, and hn and xn do not necessarily commute. So again, for the gravitationally interacting case, we arrive at a non-Hermitian effective dynamics. And the question is whether this is a feature of the Page and Buddha's framework. Maybe this is not a feature, maybe this is a bug, and we should reconsider it. Maybe it's just a general property of open systems, as Lajos implied when he traced out. And just maybe it's a hint regarding the interface between gravity and quantum mechanics. So summary until now. Time is seen as an emergent phenomenon, as claimed, for instance, by Rovelli. Time is quantized. This has been used in many approaches, so I won't name the authors. Time is relational, and this is also the Montevideo interpretation of Gambini and Pulling. And this leads us to some new time-energy uncertainty relations, to an effective non-unitary dynamics from the perspective of the internal clock, and to dynamically non-local phenomena. And I don't have much time for this last topic, so maybe I'll just give you the brief story. Some of you may know about the modular momentum operator. It is often invoked in such scenarios when we have two wave packets with a compact support, such that these two wave packets have a null inner product. And you can show that any operator of the form xn times pn for some integer n and m would not depend on the relative phase phi, but this special operator e to the power of IPL does depend on phi. Why I call it special? I call it special because in the Heisenberg picture, it evolves according to a so-called non-local equation of motion. The equation of motion of this operator depends on two remote points. And this is also different from what we see in classical mechanics. In classical mechanics, it's a local derivative. But in quantum mechanics, we have a non-local equation of motion. So what I wanted to do, I wanted to repeat this exercise in the case of time. I wanted to have non-locality in time, equation of motion which depends on two remote points in time. And indeed, using the Page and Wooter scheme and our construction of quantum clocks, we arrived eventually to an equation of motion which depends on two remote instances of time. In the paper, we gave some examples how we use it. I'm not claiming that this allows signaling. On contrast, it doesn't allow signaling. But I still find it as some curiosity. And okay, with that, I'd like to conclude. These are the works, and thank you very much.
Yeah, time for some questions.
Thank you for the very interesting talk. I had some questions regarding the construction with internal time and external time.
Sure.
And in one case, you find this energy uncertainty, energy-time uncertainty relation, and in the other case you don't.
Right.
So the first question is that, like, if the measurement, in one case you trace over the time which is inside, which is B, and in that case you get the uncertainty relation, right? Mm-hmm. Does that not mean that whatever dynamics of the clock inside the clock, you have averaged over like whatever was happening, all possibilities somehow.
Okay, so maybe I didn't explain it fully. The equation of motion in these two cases has the same left hand side. We have the time derivative of the operator TB according to time TA. And this is the internal, this is the external. The main difference is now G is a function of the operator TB, which we derive, while here G is a function of TA. So this naturally leads to a more complex dynamics, which leads to time energy uncertainty regimes, unlike this case. So you can trace it back to the tracing out of either clock A or B, but I think that here the differential equation tells the entire story.
I see, thank you.
I have a general question regarding the Page-Wouters idea. If, say, the external clock is, if you keep reading the external clock, so you continuously look at the external clock in the sense of measuring, will it freeze due to the Zeno effect?
Yes, although it's now entangled to the system, so once you project on it, you get the wave function in this time, and in this sense it's frozen, but there's no reason to now continuously measure it again. They are no longer entangled. You can add some other clocks, and you can make measurement on this clock, and then on this clock, and then...
But it's sort of an infinite series, right?
Yes. But unless you measure, you have this continuous notion of time and the full dynamical story. It's not really necessary to make the measurement.
Yeah. But I just wonder, I mean, in a way it breaks down as soon as you, in a way this idea breaks down as soon as you actually measure a clock, doesn't it?
I'm not sure. I'm not sure. First, there's the POVM approach, according to which you may continue using the same POVM. And again, you can use some multiple degrees of freedom, even of the same clock or multiple other clocks. And so I think the idea survives, it's just that the construction becomes a bit more complicated.
So we'll thank the speaker again.